Hey, we're live. Welcome to Gabversity YouTube edition. And let's see what we can do. We've got Dream, we've got Glamour. What the hell is Glamour? Hey, oh my God, that's so glamorous. And we've got Beam, whatever that is. 8mm. That's a bit weird. Dawn. All right, nah, that's fine. They're all annoying. All right, let's just go back to Beam, and now we can start. How about just normal? Yeah, let's just start with normal. So we have someone. Now, how do I find out who's watching? I can't actually tell with this thing. Finish? I don't know. Anyway, we're just starting on YouTube. This is our YouTube edition of Gabversity. If you have not seen my bracket notation episode at Gabversity on Periscope, yeah, periscope.tv/Gabversity. This is the second part in that series. I'm trying it out on YouTube to give it a go. So what we did was we already explained, if I can actually get this off, damn this thing. All right, this is not working. Excuse me for a moment. Oh, got it. Alrighty. So we're back. As we were saying earlier, we were saying that A in the bra and B in the ket together actually is sort of like two matrices being multiplied. Right, and one runs this way and it's a conjugate, and one runs this way, okay? And that's called the, it's like a transposed Hermitian, which if anyone knows what that is. All right, so what we do is matrix multiplication gives us the answer. Now, what happens if in the vector, right, you actually have a huge amount of A's? Imagine you have like 1,000,000 of them. Well, then you're gonna have to do integrals. So integral is just a way to sum up an almost infinite amount of vectors, right? And we've already done that. So let's come down to where I was. So are you ready? You ready? Let's do this. How do I change the screen? Sorry, I got to get used to YouTube. All right, so, sorry. All right, let's get used to this. Okay, so first things first. If we say that the vector A equals like A1, A2, A3, ... right? Then what we're saying, this implies that, hey, hello, Bose. I can see it. There you go. Pretty cool. So we are then implying, right, that A transpose Hermitian, or the conjugate, right, of the vector is going to equal A1 star, A2 star, A3 star, and it's going this way instead of down, right, all the way. Okay. So that's that. But now this equals, okay, it equals this. So A, okay, there it is. So basically what this does is the same notation as this, which is the same as flipping this and getting the conjugate, which is this. So what we've done is we've taken this vector, right, which is written this way, and we've flipped it horizontally. And we've made it the conjugate. Now there's a reason for that. Let me show you what it would look like without a vector. Okay, so without a vector, you would have this. You would have just A on its own. Okay. Now, if we wanted to multiply A by a number B, right, then it's just A times B. But if you had a vector, which means that you have heaps of numbers trapped within one number, which is what we call it, like a matrix, right? You might have A1, A2, A3, and then you have B1, B2, B3, right? Now, how does this work? Well, anyone who's done matrix algebra, we know that it's A1 times B1 plus A2 times B2 plus A3 times B3. That's how that works. And that's why it's written that way. So what we can do, right, is we could say that we want to multiply A by B, okay? In this case, we have two columns. We have A1, A2, A3, ... and we also have B1, B2, B3, ... Okay. Now you can't multiply them like that. That's why you got to flip this one horizontally, and then you conjugate it. The conjugate you don't need to do, but we have to do it what do you call it, for quantum mechanics, right? And so that's why this automatically implies that that is the conjugate and transposed, and that's called the Hermitian. So there you go. That answers that. So the other side is just the column. So we said that if we were to flip that vector, okay, if we wanted to do this, which is to flip it horizontally and then make it a conjugate, then we put it in this notation, okay? All right, and that's the bra. Now, the ket is the other side, which is like when you had B, it was just B, so it went all the way down. So that's just this B, like that. All right, now when you put them together, you get this. You get the bracket, see? A. I know it's not really original in terms of its notation. So there it is there. All right, beautiful. Okay. So now let's move on. So what we're going to say, all right, is, let's have a look at this. Let me find you some stuff. I'm trying to find you actually stuff that's actually important. All right, operations revisited. Blah, 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 blah. Sorry, I'm trying to find you what's actually important. Okay, here we go. So, oh, come on. All right, this was a good test. Oh, we have one person. There you go. So I think that's basically it. I don't think there's anything else I want to tell you. Hello. Hey, just checking comment. 5:49 p.m. Yeah, I saw that actually. All right, so we're back. Now, what were we talking about? Projection operators. All right, the operator maps any vector V, element of V, to a vector along the other one at the comma. Indeed, acting on V makes it a certain thing. All right, so that's just projection stuff. Yeah, looks like I should have been able to plan this a bit better. But hey, that's why I'm doing it on YouTube, where I have the least amount of followers. Adjoint of a linear operator. All right. This stuff is so boring, honestly. Honestly, I've got to make it more interesting, but it just drives me crazy. Hermitian and unitary operators. So, blah, blah, blah. There we go. That's what I wanted. All right. So this, for a wave function, is what I wanted to show you guys. All right. So let's say we have a wave F and we have another one G, and we put them in the bracket notation. This is the same as doing this. Integral from minus infinity to infinity. I don't think you can make it more so. Unfortunately, yeah, I'm trying. Right? Which is f of x, right? Conjugate, and then g of x dx. Now, in all of the other